Exploding stars, or supernovae, are some of the most powerful events in the universe. When a star runs out of fuel, it can no longer produce energy to counteract its own gravity, causing it to collapse in on itself and explode in a spectacular display. Cassiopeia A, or SOS A for short, is one such supernova remnant. It's located about 11,000 light-years away in the constellation Cassiopeia. It's the result of a massive star that ran out of fuel and exploded around 350 years ago. Scientists have been studying SOS A for decades, but there is still much we don't know about this cosmic object. Its complex structure and different layers have puzzled researchers, and its behavior and evolution over time are still being studied. Enter the James Webb Space Telescope, or JWST for short. This revolutionary telescope, which was launched on December 25, 2021, is set to change the game when it comes to observing the universe. With its advanced technology and capabilities, the JWST is perfectly suited to study SOS A in detail. Its infrared sensors can penetrate the dust and gas that obscures the supernova remnant, allowing us to see it in a new light.
MIRI is one of the 4 instruments on board the James Webb Space Telescope. It's the one instrument on board the telescope that will be observing at mid-infrared wavelengths. The other instruments focus on the near-infrared part of the spectrum.
NIRSpec, NIRCam and the FGS, they work at wavelengths from about 1 to 4 or 5 microns. Now MIRI is unique on the James Webb because it operates at even longer wavelengths than that. So we start at 5 microns and we keep going out to 25, 30 microns.
MIRI is actually quite a complex instrument. It has several different observing modes on board in the instrument. So we have a camera that just takes images in lots of different filters across the mid-infrared wavelength range. We also have spectroscopic modes, so we have low-resolution spectroscopy, and we also have a medium-resolution integral field spectrograph.
When you look inside our own galaxy, you can see dusty regions, and there's things going on inside those clouds, inside the dust, that you can't see because dust is essentially opaque. If you move out to longer wavelengths, out into the infrared, the opacity, the amount of light that is absorbed by that dust drops, and so we can see not just the surface, but into the heart of dusty region. So that means we can see to the center of our own galaxy more easily. We can see inside dusty regions where stars are being formed and see them, see what's really going on when a star is formed in space.
We're really going to be able to address a huge range of science questions. MIRI is going to be able to probe even further back into the history of the universe. It's going to be able to really study the atmospheres of planets around other stars and really be able to kind of search for the signatures of molecules in those atmospheres. Those are just a few of the highest kind of profile science goals that we hope to achieve with MIRI.
Already, the JWST has captured stunning images of SOS A, revealing new details about its structure and composition. But there is still much more to be discovered, and scientists are eagerly anticipating the data that the JWST will continue to provide. Thanks to the James Webb Space Telescope, we are one step closer to unraveling the mysteries of the Cassiopeia A supernova remnant and unlocking the secrets of the universe.